was, P.S. we don't like H anymore and we want you to get rid of him. By the way, we gave you this clue that relates H with R, so use that clue to get H alone to substitute in to get the equation only with R's. They didn't tell you any of that. But that's exactly what you had to do. So then when you come on down and read the directions, find the volume of the can as a function of the height H, what's the understood directions in this if the formula right now is V equals pi r squared H? Or you could say V equals 4 pi r cubed. Both of them are right, but what's the direction, or what's the final answer they actually want in letter B? Or what do they want it to look like? F of H. So in letter A, they wanted V equals F of R, which equals 4 pi r cubed. That was the final answer for letter A. They wanted you to take this guy who has radius and height, and of course like a pi and a squared, and say use that clue, use this ratio, to basically substitute out the H in terms of R, and then be like, oh yay, function of R. Volume is only dependent on the radius variable. But now all of a sudden they're like, no, 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 no. They're being a little bit fickle. Now they want F of H. So anybody see anything that'll help us get to that? H equals 4R, or H over R equals 4. How can we use these to help us get here? Okay. So do you want to get rid of the R in the original equation, the OG, or in the transformed equation? Doesn't matter. Which one do you guys want to go for? Okay, so let's go here, because we have all our variables in one place, R, but we don't want R anymore. So what can we plug in for R? Yeah. Couldn't we get R alone now? Which one makes more sense to your guys' head saying it? H over 4 or 1/4 H? Which one makes more sense? Okay, so then we'll do H over 4. Just a heads up, a lot of you guys, 1/4 H probably makes a little bit more sense. Don't just go with what we say. But yeah, I'll use H over 4 because those are the first ones. Robert and Kyle both said that. So let's take this one, 4 pi. We have H over 4 cubed. How do we simplify? Why are we simplifying? Do you see how there's a 4 here and there's a 4 there? Now careful, if we just cross out, that's horribly illegal. We could kind of say that kittens have died. That's having to do with just like crossing stuff out in a fraction without really thinking about it. Why can't we just cross out the 4s? There's a cubed. So how do we do the cubed? What can we say? Cubed root is if we wanted to move it to the other side, but do we really want to cube root the V? No. We could split it up. Wouldn't this be the same thing as, just for those of you that are like, I don't see it? Isn't it just H over 4 cubed? And what's H times H times H? What's H cubed? H cubed. What's 4 times 4 times 4? 64. So we could go ahead and do 4 over 64 pi H cubed. Wait a minute, why did I put the over 64 over here? They go together, they're coefficients. Yeah, I can simplify better, which is why I thought some of you guys, the 1/4 H might be nicer. Because then you would have 4 times pi times 1/64 times H cubed. It might have just made a little more sense. But that's okay, we still end up in the same place where 4 over 64, any mental mathers out there, reduces to be? Yeah, you can also think one of the 4's reduces and we have 4 times 4 left. We can do 1/16 pi H cubed. That would have been totally fine to write as pi H cubed over 16. But either way, now we have V as a function of H. But what was the key to solving for both of these? First of all, having an equation, right? We had to get an equation first. Had to find or review or remember an equation first. Then exactly the ratio. The clue in the problem itself that let us make this little relationship between H and R that we used over and over again, either to get rid of the R or to get rid of the H. So function of says, hey, I want the equation only in terms of, so somehow substitute out the other one. Substitute away the other one. Did anybody get up to homework to any word problems that were similar to this? Okay. I think it was towards the end of homework, and you guys probably stopped somewhere in between. I'm saying stop somewhere in between because what was homework over the weekend? To do test corrections, quiz corrections, and start. Thank you. And I'm assuming honors kids started their homework like they were supposed to. All right. Let's talk some more about function stuff. Let's get back to some more basics. Don't give up on those word problems on me. But read them very carefully because all the words have meaning and are little clues as to what you're supposed to do. Did any of your Algebra 1 teachers give you a trick as to how to remember domain goes with X and range goes with Y? Does this ring any bells that domain goes with X and range goes with Y? Okay. Super silly way of remembering it. Range is actually the hardest one by far. Domain, if you just memorize a few different, like, hey, watch out for, and do this if you see. Denominators, square roots, logarithms. Trig functions that are nasty. That's it. Those are the 4 ways that domain can be anything or needs to be anything other than all real numbers. Domain you can memorize. Certain things to watch out for and what to do if you see them. Range, you kind of have to visualize a graph, and graphs can get all sorts of nasty. So just in case you're like, oh, domain, I hate that one. No, you should learn to love that one between the two because he's one that you can do every time as long as you figure out the domain problems is what I call them. But the way I remember them, it's super silly, I know. As I think of why is that yellow, I don't know. Yeah, I did, and then it just kind of kept it. My mom used to work in a doctor's office. And the best part of that, she was like a receptionist in the front for a surgeon, would be all the free things that like the pharmaceutical reps would give her. I don't know if any of your parents work in the medical field, but they have all these pens and like notepads and I don't know, all these different things that she'd come bringing home. This sounds totally like a medicine to me, Domain-X, like one of those like Domain-X, and with all these little, what at the end of commercials, like, oh, by the way, you might die, like have fun taking it. Anyway. So Domain-X sounds like a medicine to me, and then range, not that it's on this page at all. But I always talk about the cute little rangy. Oh, the little rangy. So the rangy, and then the Domain-X, I don't know, it's super silly, but if no one ever taught you a way to memorize which one goes with which, Domain-X sounds like a medicine, rangy, oh, he's cute. Although he's not, he's actually quite a pain. Although cute little things are usually pains. But anyway, coming back. Domain-X and rangy. I know it's silly, but when I taught Algebra 1 back in the day, it was actually the way I learned in high school. Middle school? Middle school. But coming back to domain, Domain-X. Domain, the set of all possible x values for a function. Basically, which x's are allowed and which x's will be used. I want you guys to think of, we're going to go way more in depth in this later. If you're looking at a graph, I want you to think how left to how right. That's a gross simplification, but it is super helpful as far as visualizing. Because remember, sometimes you have to deal with graphs. And if you're looking at a graph like a big old XY and you're trying to look at a function and say, I wonder what its domain is. And let's go a little bit crazier because you guys are honors. Let's say we have an ln function. Hold on, pause. Kim, can you see this? You can't see on that side. Okay, thanks. Let's go over here then. You guys know the 4 keys to success, right? Should be a bonus on something. Anyway. Okay. What do you think is going on x equals 0? Ooh, what is x equals 0? A vertical line or horizontal line? equals 0. Yeah, there's no slope because y equals mx. Oh, there's no y. Oh, no, the slope's undefined. What's going on at x equals 0 is a vertical asymptote. This is actually the function y equals ln of x. This is kind of a little premature, but that's okay. My question to you is, what's the domain of this function? And look at what I just wrote. How left to how right. If I was to start somewhere in the middle of this guy and start going left, how left can I go? I can go towards 0, towards 0, towards 0, towards 0, towards 0, towards 0, never touching. So how left can it go? 0, but never touching. How right can it go? Forever. So you could put this a couple different ways. You could say x is greater than 0. Why not or equal to? It never touches. So I could just say x greater than 0, and greater than just means everything greater than, right? Or the other way of thinking about it, when we learn interval notation, when we review interval notation, we looked at it just a little bit in our graphing calculator handbook. Intervals always need left to right or how low to high. So how left would be 0, technically a parenthesis because it's not or equal to. The comma says from 0 to what ending point? We would say infinity. Don't worry, interval notation, we'll get to it later. But just the idea of how left to how right, domain, the x values moving along the x-axis, and asking ourselves how left to how right. There are two different ways domain can happen. One of them is it's actually stated for you. For instance, what if you were given, I don't know, a set of points, a relation, maybe a function. And let's say they give you something like -1, 1, 3, 4, 2, 7, and 5, 1. First of all, is that a function or a relation or both? Is it best to call this a relation or a function? What would you guys say? Function, yes. Why? Passes the vertical line test since each and every x is paired with one and only one y, or no x is repeated with a different y. So yes, it is a function. That's true. F function. Functions are fun. Just kidding. But what would the domain be? Not all real numbers. Good guess, though. I don't see any problems except... Well, that one x wasn't allowed to be negative, but there's nothing saying x can't be negative, no square roots. How many points are there to this function? Only 4. You just gave me an infinite answer. So what would the domain be? It's not infinite, there are only 4 points. It's so easy, it's hard. You could do a little set builder notation with a little like x's. Did you guys see that last year? A little bit like all values of x such that x is equal to. You could do a set builder notation. See what I mean by it's so easy, it's hard? So if you're looking at a graph, you go ahead and, let me get a little more space so I can put the answer up there. If you're looking at a graph, you think of how left, how right. You think of inequalities and infinite answers. But if they give you like a set of ordered pairs, you're really just saying, well, who are the x's? Asking yourself the question, are there infinitely many points? No, there's only 4. Okay. Well, then the domain is just those 4 x's. What would the range be then of this function? Yeah, 1, 4, 7, and 1. 1's repeated. Don't write it twice. 1, 4, 7. Yeah, that would be the range, but that's not this slide. So one way is that they give you a certain amount of data and it's stated for you. They can also do things like, remember the piecewise functions in the graphing calculator handbook? And how for the piecewise functions, you had that big old brace, and then it said x is less than or equal to 0, and x is greater than 0. That's defining the domain for each piece. But there is another type of domain, and this is the one that we're going to see most often, implied domain. We need to analyze the function because the domain is implied based on the nature of the function. And so let me give you a basic example that seems to confuse people. What if I give you y is equal to x squared? Doesn't look too bad. He's a parabola. You guys could probably at least sketch me a graph of him really fast, right? With the points 0, 0, 1, 1, 2, 4, 3, 9, 4, 5, 25. Going the opposite way, negative 1, 1, negative 2, 4, negative 3, 9. What makes them hard? I don't know. Some people just kind of get stuck on the easy ones. Domain, if it's not a graph, how left, how right. If it's not a set of ordered pairs where we just steal the x's, if it's a function, we have to ask ourselves the question, what x's work when you plug in? Or similarly, what x's don't work if you were to plug them in? All x's work? What if you plug in a positive number? You can square it. What if you plug in a negative number? You can square it. What if you plug in 0? You can square it. It's 0. Whatever x's you plug in, you're going to have y's that are real, that exist, so therefore the domain is super simple, all real numbers. Have you guys seen the notation? Okay. You can do set builder notation, all values x such that x is within all real numbers. You can actually say the statement all reals or all real numbers. But it's implied based on the function. The parabola goes forever left, forever right. I mean, it goes up high, but it's going to keep on expanding. And if you look at the function itself, I can plug in negatives, I can plug in 0, I can plug in positives. Now what changes as soon as I say y is equal to the square root of x? Negatives are good or negatives are bad? Bad, because those are imaginary. When, or those results in imaginary, when you put them under a square root. So if x can't be negative, how could we state the domain? X is equal to 1, 2, 3, 4, 5. What about 1.1 and 2.01 and 3.0001? All positives, so we could write x as all positives, but what's the number that's in between negatives and positives and doesn't exactly have a label? Can I take the square root of 0? Yeah. What's the square root of 0? Because 0 squared is. So therefore, we could say x is greater than or equal to 0. But what made the difference between this domain of all real numbers and this domain of x greater than or equal to 0? They didn't tell you. It was implied based on the function. Does that make sense? And this is where it gets hard, because they can't always tell you what the domain is. You have to get to know these functions so well, you know what's legal and what's not. Does that make sense? Kind of like, how many of you guys have permits or licenses? Okay. How many of you guys want a permit sometime soon? There you go. Okay. So, why is there something called driver's ed? Because you don't have Siri in your car every time you turn on the engine telling you exactly what you're supposed to do and what you're supposed to remember, and you're supposed to learn those things so they're second nature and they just come to you, right? Because if you're opening your driver's ed manual as you're on the street trying to figure out what to do when there's like a green light and then you have someone coming towards you and it's not an arrow but you're wanting to turn left, or if you're doing like a blind intersection sort of thing, or if you're parking on if you're parking a car on a hill, yep, and then your brakes might fail and then you might go back and like kill people, right? Those aren't things that you're supposed to pull out your manual and then go looking. Those aren't things that necessarily are supposed to be written all over your car in little post-its so you don't forget. Those are things that you're supposed to study and then remember when you need to access them, because it's like a split-second decision. That's what these need to be. They're implied. So hopefully we'll get so used to these functions that you'll just kind of get to the point where you can look at them and say, oh, it's easy. I know that that's the only x's that are allowed. Because we want to do what's legal and what's not illegal. Life lesson to that, but let's come here. So I just said a second ago, it's important for us to be able to look at a function and know when the domain has no problems, all real numbers, like x can be anything, or look at a function and see, oh, wait, you know what, we're going to have some issues if x is. So for right now, I haven't even added on the trigonometric stuff because we're not doing trig yet. And they're vertical asymptotes for tangent and cotangent and secant and cosecant. Sokotoa choshakao. But I did put logarithms up just so that you guys, because I already did an ln up on the board. I I did put logarithms up just so that we can at least peek at him. But once again, he's not going to be needed yet. We're kind of building up to this. But what we did already talk about are roots. Now question, why did I put even powered? Can anybody figure that out? Come on. Think deeply. Why not odd powered? Why just evened? So whether you have a square root of x, or a fourth root of x, or a sixth root, or an eighth root, or a 12th root, or a 14th root, 10th root, I think I missed it. Yeah. Just real quick off to the side in case you're wondering, the domain for y equals the cubed root is all real numbers. How come? Yeah. Because what's a negative 2 times a negative 2 times a negative 2? Negative 2 cubed is what kind of number? It is 8, but it's not just 8. It's negative 2 times negative 2 times negative 2. It's a negative 8. Can't you put negative numbers underneath a cubed root and have it totally work? Ooh, that's bad. Now it's good. Right? So negative numbers work, 0 works, positive numbers work. So if it's a fifth root or a seventh root or a ninth root, totally fine. Because you're going to have an odd pairing of negatives to make a negative or an odd pairing of positives to make a positive. I don't care. But as soon as I have a square root or a fourth root, can I have an even pairing of negatives to make a negative? Nope, because a negative times a negative will always be a positive. So if I have even pairs of numbers, negatives times negatives will always be positives. Which is why for any root, the domain problem instead of greater than or equal to 0. Whether it's a squared root, whether it's a fourth or a sixth or an eighth or a 10th. The domain problem is that the argument must be greater than or equal to 0. And just for sake of argument, I'm going to go ahead and put a little fourth root just as my example. But what if I was to go ahead and give you the following? What is the domain? For y equals the square root, and let's use the fourth root, of 2x plus 1. It's a little harder just on top of your head to be like, oh, when is that positive? Oh, when is that negative? But I just gave you the key. You don't even need your calculator because here's why. I just said whatever is the argument of the function. Another way of saying it is whatever is the radicand or whatever is underneath the radical. Whatever is the radicand, whatever is underneath the radical. So if you want to call it the radicand, you can change that too. The argument of the radical or the radicand, which is always whatever is underneath, radical, radicand. Just set it greater than or equal to 0. So what happens when we set 2x plus 1? That's my domain. I can stop? No, you got to get x alone. But how do we get x alone? Oh, not add. Subtract the 1 and then? Oh, and that's pretty easy because your domain is just going to be x is greater than or equal to negative 1/2. Pause, real quick reminder. What do we do when we multiply or divide inequalities by negatives? Okay, just in case it shows up, you always have to flip the inequality if you multiply or divide by a negative number. But in this one, where did the negative come from? Just the subtraction. So we didn't flip it, we didn't have to. If worst comes to worst, you can always test by plugging in what's a number greater than or equal to negative 1/2? 0? 2 times 0 plus 1, it works. What's a number less than negative 1/2? Negative 1. 2 times negative 1 is negative 2 plus 1. Oh, yeah, it doesn't work. Okay, good. I have it go in the right direction. Denominators, what's the problem with them? So let's say we had an f of x over a g of x. 0 is the problem, but how is 0 the problem? Who's not allowed to be 0? The denominator. So I'm going to say denominator cannot equal 0. If you guys don't like the whole notation-y thing, you can literally just write denominator can't be 0. Just like I said, the radicand can't be 0. So whenever you see denominators, take that denominator, set them not equal to 0. So if I were to give you the example, find the domain for y is equal to 2x over it won't be that mean. Let's just do 3 minus 2x squared. Is that one an easy one off the top of your head? Oh, of course, x can't be. This isn't even one that we can factor because we don't have like an x squared and an x and a single. Because usually we factor to find zeros. So how would we find the domain? Follow the clue, and the clue says, hey buddy, you can't be 0. Sweet, how do we solve then? Do some algebra. Subtract 3, divide by a -2, and then plus or minus square root. So that'll lead us to x cannot equal, okay, follow the logic. Remember, if you're trying to get to the x squared, you gotta start by picking off the guys farther away from him. So then x is equal to, subtract the 3, divide by -2. Wouldn't that be 3 halves? And plus or minus square root of 3 halves. Now if we're amazing Algebra 2 students, we would go ahead and rationalize that radical. So we would have times root 2 over root 2, which would be root 6. Oh dear. Root 6 over 2. You guys remember rationalizing your denominator? Wrong piece. Square roots of fractions split up to be square root of top over square root of the bottom. So I would need to do a little multiply by root 2 over root 2. Square root 2 is square root 4, which is just 2. I've gotten rid of the radical down there. And root 3 times root 2 is root 6. There's properties with square roots, especially with fractions, that we kind of forget about, but that would be our final answer. You could get decimals, I suppose, but for the most part, I like keeping everything exact and precise, because as soon as you have a decimal, you round, and as soon as you round, you introduce error. This little square root of 3 halves is the same thing as root 3 over root 2, and in Algebra 2 we learned you shouldn't leave square roots in denominators. And so to get rid of square roots in denominators is we take whatever is in the denominator, which is 2, and I multiply top and bottom by that radical. And if you were to think fractions, you multiply tops and bottoms. Everybody has a square root, so they get to all combine. I would get root 6 over root 4, and root 4 is 2. Yeah. Logarithms, you won't need it for this section, but if you were to have any log of any base of any argument, I'll just put an x for right now. The domain of this guy is going to be the argument of the logarithm. Has to be greater than 0. Now, here's why this guy is tricky. Doesn't this look an awful lot like the first one? Yeah. A lot of pre-calc kids, or even Algebra 2 kids, or even calculus kids, get confused as to which one's or equal to and which one's not. But if you guys look at this, square root of 0 is totally fine. But ln, or any logarithm that's non-translated, not been shifted, every logarithm is saying, I can't hit my vertical asymptote. So logarithms say, I get closer and closer and closer and closer, but never touch. That's why it's greater than 0. Radicals are like, give me a 0. I don't care. If I'm not in a denominator, I'm in a denominator. But if he's not in a denominator, radicals are totally allowed to be 0. Logarithms aren't, as far as the arguments. Now, I know that you're like, oh my goodness, we were supposed to finish section 1.4 today. I think we'd be okay with all of these based on what we've just done. But the problem is we didn't talk about range or f of x function notation. So our calendar online is correct in that we're going to need to take one more day on section 1.4. Yeah. So if you didn't start homework over the weekend, now what do you need to do? Start. Because if I'm taking 3 days on this section, it's a doozy. You guys got it? All right. So homework is going to be, I'm coming back to the board. Our calendar online is right. Not due tomorrow. It'll be due on Wednesday. So some of you are lucky. You don't have to finish it tonight, but you do need to start it. Who knows? Maybe I'll do a start spot check tomorrow and see if you did. All right, cool kids. Chapel day. I think that was 9:30, right? Wait a minute. No, I'm right. Yeah. Why is it so quiet outside? Right? Are you guys? This is weird. Ah! All the high schoolers. Teachers must have let them out late. Yeah, get out of here.
Get out of here.
Thank you, thank you. Oh, Rachel, that is gorgeous. Thank you. It was so quiet outside. I thought I was wrong.
I did start though.
Good, 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 good. Not sure if you'll be able to go tons farther, but domain is so important, so people always forget it.
News.
Yes.
Brother came back.